Hello again. We're going to finish up our discussion of improper integrals by talking about how to approximate those improper integrals. All right. So let's say I have a graph like this, and I want to find the improper integral of it from some x all the way up to infinity. But let's say that it can't be evaluated because I don't know what the antiderivative is, or no one knows what the antiderivative is because it doesn't exist. So what we have to do is we have to approximate the area under the curve. And we do that using what are called Riemann sums. Okay, so those are basically a bunch of rectangles, and I've made my rectangles exactly 1 unit wide, and then the height of each rectangle corresponds to a function value on that curve, one of the dots on the curve. So with left-hand rectangles, the height of the rectangle is represented by that dot that is in the top left corner of the rectangle. If I want to use right-hand rectangles, then the height of the rectangle is represented by the function value in the top right corner of that rectangle. All right, so notice that the heights of the rectangles of the second left-hand rectangle is the same as the first right-hand rectangle. That's always the case. And the third left-hand rectangle has the same height as the second right-hand rectangle. And this goes on in a pattern. Okay? So in fact, if I move all of those rectangles, those right-hand rectangles, if I slide those over one, they line up perfectly with the left-hand rectangles. Okay, so if I want to approximate that area under that curve, the left-hand sum is going to be the sum from a to infinity of the function values. Because remember, the width is 1, so I'm taking that width and multiplying it by the function value from a to infinity, wherever I happen to be starting. Then with the right-hand sum, I'm always starting at the next or the second rectangle if it was the left-hand sums. So basically, the right-hand sum is going to be everything except for the first rectangle in the left-hand sum, if that makes sense. All right, so I see that this function is decreasing. So even if you look at the rectangles, you'll see that all of those rectangles are below the curve. So that's going to give me a lower bound on what the area actually is. The left-hand sum is going to give me an upper bound in this case because the function is decreasing. All right, so the right-hand sum will always be less than the actual area, and that will always be less than the left-hand sum. Now, let's say the function is increasing instead. The left-hand sum is going to be a lower bound because even though those rectangles go beyond the curve, and you might think that that's an overestimate of the area, remember that the areas of those rectangles are technically negative. So the area of those rectangles is more negative than the area under the curve. So just it's kind of a hard thing to grasp the concept of, but with more examples, we'll see that that's true. And similarly, the right-hand sum is going to represent an upper bound because those areas are actually less negative than the area under the curve. Okay, so if that makes sense. All right, so what that means is now the left-hand sum is going to be less than the actual area, and that's going to be less than the right-hand sum. All right, so let's look at an example. I'm finding an upper and lower bound for 0.8 to the x. Now 0.8 to the x, that's something that I can find the antiderivative of. But I'm just going over a concept, so I wanted to start off with a simpler example where I didn't have to plug something into something that was way too complicated. All right, so I'm doing 0.8 to the x. The function is decreasing, so the left-hand sum is going to be an upper bound, and the right-hand sum is going to be a lower bound. So let's look at the sum of those rectangles. Well, the first rectangle is going to go all the way up to 0.8 to the 4. The next one's going to go all the way up to 0.8 to the 5, whatever those values are. Okay, and there's those values right there, 0.4096 plus blah, blah, blah. So I need to add all of those up. But if I notice, even if I'm looking at when I wrote it as 0.8 to different exponents, this is an infinite geometric sum. It's geometric because I keep multiplying by 0.8 over and over again to get from term to term, and it's infinite because it does go on forever. So I need to add all these up, and I can do that by using the formula for infinite geometric sums, which is a over 1 minus r, and that gives me 2.048. So that is the upper bound of the actual area. Now the right-hand sum is my lower bound. And notice that those areas are exactly the same as the left-hand areas without the first rectangle. Okay, so I'm starting at 0.8 to the 5 and then 0.8 to the 6 instead of starting at 0.8 to the 4. So that first rectangle is gone. Okay, so what I can do is I can just take that upper bound, 2.048, and subtract off the first rectangle, which was 0.4096. And I get 1.6384 as my lower bound. All right, so that means that the actual area is somewhere between 1.6384 and 2.048. All right, here's an example of a function that is increasing. So we'll see what we mean when we say that the left-hand bound is actually, or the left-hand sum is actually a lower bound and the right hand is an upper bound. So this function is increasing. I'm doing -4 to the negative x. Again, I could find the antiderivative of that, but again, I'm just using simple examples so that you get the concept. There's the left-hand sum, and that is the first rectangle has an area of -4 to the -1. The next one has an area of -4 to the -2, and so on. Okay, so that's -1/4, -1/16, and so on off to infinity. And this is another infinite geometric sum. So I use my formula again of a over 1 minus r, and I get -1/3 as the lower bound for my area. Then when I use my right-hand sum, again, I notice that those rectangles have the same area as the left-hand rectangles without the first rectangle. All right. So all I have to do is take the sum that I got for the left-hand sum, which was -1/3, and subtract off the first left-hand rectangle, which was -1/4. So if I have -1/3 and I subtract off -1/4, I get -1/12. So what that means is the actual area is somewhere between -1/3 and -1/12. All right, so that is approximating improper integrals. If you have any questions, please let me know, and I will see you tomorrow.